Have you ever looked up at the night sky and wondered what's really out there? We see stars, galaxies, planets, but what if I told you that everything we see, everything we've ever detected, makes up less than 5% of the entire universe? For years, scientists have been grappling with one of the universe's most perplexing riddles. It's a puzzle that keeps cosmologists awake at night. What is dark matter? Join me as we embark on a mind-bending journey, unraveling the evidence, the theories, and the profound implications of this elusive cosmic component for our understanding of the universe's past, present, and future. So, where did this crazy idea of dark matter even come from? It all started back in the 1930s with a brilliant and somewhat eccentric astronomer named Fritz Zwicky. He was observing the Coma cluster, a massive group of galaxies, and noticed something was off. The galaxies were moving way too fast. Based on the amount of visible matter, the stars and gas, he could see that gravitational pull should have been strong enough to hold the cluster together. These galaxies should have been flinging themselves out into the void of space. Zwicky proposed that there must be some unseen, dark matter providing the extra gravitational glue. At the time, his idea was largely dismissed. It was just too radical. Fast forward a few decades to the 1970s, and enter the legendary astronomer Vera Rubin. She was studying the rotation of individual spiral galaxies, including our own neighbor, Andromeda. According to our understanding of gravity, stars farther from the galactic center should orbit more slowly, just like Neptune orbits the Sun much slower than Mercury does. But that's not what she found. Instead, she discovered that stars on the outer edges of galaxies were moving just as fast as those near the center. This flat rotation curve was a huge shock. It was like watching a merry-go-round where the horses on the outside are keeping pace with the ones in the middle. The only way to explain this was if there was a massive, invisible halo of matter surrounding the entire galaxy, extending far beyond the visible stars. Vera Rubin's meticulous work provided undeniable evidence that Zwicky was onto something. Dark matter wasn't just a quirky idea anymore, it was a cosmic necessity. But how do we know it's there if we can't see it? Well, besides making galaxies spin faster than they should, dark matter leaves other fingerprints on the cosmos. One of the most powerful tools we have for detecting it is something called gravitational lensing. Think of it this way. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time. So, if you have a massive cluster of galaxies, its immense gravity can act like a giant cosmic magnifying glass. The light from a more distant galaxy behind it gets bent and distorted as it passes by. By measuring how much this light is bent, astronomers can calculate the total mass of the cluster. And time again the results show there's far more mass than we can account for with visible matter alone. The extra mass, the source of that extra gravity, is dark matter. It's like weighing a bag of groceries just by seeing how much it stretches the bag, without ever looking inside. So we have all this evidence, but the multi-trillion-dollar question remains. What asterisk is it? This is where things get really interesting and, I'll admit, a little weird. The most popular candidates for dark matter are hypothetical particles called WIMPs, which stands for weakly interacting massive particles. The name says it all. They are massive, which explains their gravitational influence. But they interact very weakly with normal matter and light, which is why we can't see them. They would pass right through you, me, and the entire Earth without leaving a trace. Except for their gravitational pull. Scientists are building incredibly sensitive detectors deep underground, shielded from cosmic rays and other noise, hoping to catch the faint signal of a WIMP bouncing off a nucleus of an atom. Experiments like LUX-Zeppelin in the US and Xenant in Italy are in a race to get that first direct detection. Imagine the moment we finally capture a ghost particle that makes up a quarter of our universe. But WIMPs aren't the only game in town. Some physicists favor another candidate called the axion. Axions are predicted to be incredibly light, trillions of times lighter than an electron, but there would be an absolutely enormous number of them swarming through space, collectively creating the gravitational effects we observe. Experiments like the Axion Dark Matter Experiment, or a DMX, use powerful magnetic fields and microwave cavities to try and convert these hypothetical axions into detectable photons. It's like trying to tune a radio to a very specific, very faint frequency that no one has ever heard before. Other more exotic theories propose that dark matter could be made of primordial black holes formed in the first second after the Big Bang, or even that our understanding of gravity itself is incomplete, a theory known as MOND or modified Newtonian dynamics. This would mean we don't need dark matter at all, just new laws of physics. Each of these possibilities opens up a whole new can of cosmic worms. So why should we care about some invisible stuff floating around in space? Because understanding dark matter is fundamental to understanding our own cosmic origins and destiny. The large-scale structure of the universe, the vast web of galaxies and clusters we see today, was sculpted by dark matter. In the early universe, tiny fluctuations in the density of dark matter acted as gravitational seeds. Normal matter was then drawn into these gravity wells, eventually collapsing to form the first stars and galaxies. Without dark matter, the universe would look completely different. There might be no galaxies, no stars, no planets, and certainly no us. Dark matter is the invisible scaffolding upon which our luminous universe is built. Furthermore, the ultimate fate of the universe is tied to its total mass and energy content. Will the universe expand forever? Will it eventually slow down and collapse back on itself in a big crunch? Or will it be torn apart by a mysterious force called dark energy? The amount of dark matter in the cosmos is a critical piece of this puzzle. By pinning down its properties, we can get a much clearer picture of where the universe is headed over the next trillions of years. We're not just solving a riddle about the present, we're reading the first and last chapters of the cosmic story. It's a profound quest to understand our place in the grand scheme of things, from Fritz Zwicky's bold hypothesis to Vera Rubin's groundbreaking observations, and now to the massive underground experiment searching for ghost particles. The hunt for dark matter is one of the greatest scientific adventures of our time. It pushes the boundaries of our technology and challenges the limits of our imagination. It reminds us that the universe is far stranger and more mysterious than it appears. What we see with our eyes is just the tip of the cosmic iceberg. The next major breakthrough could come tomorrow, from a lab deep underground or a telescope peering into the deepest reaches of space. And it will fundamentally change our understanding of reality itself. Thank you so much for joining me on this journey through the invisible universe. It's a mind-bending topic, but it shows how much there is still left to discover. If you enjoyed this cosmic exploration and want to learn more about the mysteries of our universe, make sure to hit that like button, subscribe to the channel, and ring the notification bell so you don't miss our next adventure. What do you think dark matter could be? Let me know your theories in the comments below. Until next time, stay curious.